Okay, so let me review so this is lecture 3. We're discussing the TTT correlation function in CFT and trying to understand why there's a class of theories where this agrees with Einstein gravity. So this is the simplest way. This is the simplest, or seemingly the simplest question you can ask of how you get Einstein gravity out of CFT. And let me sort of review the set of ingredients that we discussed so far and that we want to pull together in this last hour. Okay, so there's, first of all, I want to distinguish between the operator conditions and the OP coefficient conditions. Okay, so first of all, there's the NAC, which is the statement that this operator is positive, and this applies in any conformal field theory. And then there's a particular consequence of the NAC, which comes from evaluating the NAC inside a state created by an insertion of a wave packet of the energy momentum tensor. Okay, so that gives the conformal collider bounds or Hoffmann-Matosena bounds, and in particular restricts A over C to this range of values. Now, so this was completely general. It's the NAC is really the stronger condition, and this is a consequence for the TTT 3-point function. And then if we take large N so that was any CFT. If we now take large N and a large gap, then both of these things become stronger. So here for the OP coefficients, we said that from a bulk analysis, we know that this range should collapse down to just 1, and then you have to have A equal to C up to small corrections. And that came from studying causality in the bulk shock wave. There should be some operator that's positive that strengthens the NAC in holographic theories. And that's that's what I want to explain, is what is this operator that's responsible for this constraint. And once we've found that operator, we want to use it to prove this universal coefficient. Okay, so and here is the picture to remind you of the bulk experiment that led to this constraint. It came from looking at gravitons. So this here is a graviton, which is propagating parallel to the ADS boundary. In some excited state, I didn't draw the excited state this time. There's some excited state, and the graviton is propagating parallel to the boundary. Okay, so that is the setup, and what I'm going to explain now is what is this operator, where does it come from in CFT, and why am I calling it the length operator? Okay, so let's see.
So from the bulk, you always get A equal to C, right? That is just a purely field theory comparison.
Sorry, what? This?
That one is just a field theory.
Well, right. So in field theory, if you have the NAC, then purely in field theory you get this.
But from the bulk, I don't get. Just from the bulk, A is equal to C always,
right? Right. Well, from the bulk, you get this at large impact parameter and this at small impact parameter.
Why from the bulk should I? So I'm a bit confused. Why from the bulk? I thought at large N, if I have ADS safety, it's large N and large gap, right? Already.
Yes, but
so why should I get that?
Well, I mean, this is true in any CFT. So in particular, it's true in holographic CFTs. That's one way to think about it. Another way to think about it is that, as we're going to see, this is all properties of the OPE. So if you do some holographic experiment that's very close to the boundary, then the answer that you get is actually just a property of the OPE and can be true in all theories, not just holographic theories.
You know, I think Sachin's saying it's already Einstein gravity.
Yeah.
I think the game would be, for instance, take Einstein gravity and then add a Gauss-Bonnet coefficient. And check how the Gauss-Bonnet coefficient, for instance, is constrained. And Tom said, if you do
Oh, I see. Sorry. Yeah.
I see.
So I'm saying if you do the experiment far away, it would constrain it, the Gauss-Bonnet coefficient in such a way to ensure that. When
Right.
you do the experiment nearby, it will do this.
I see.
Right.
So just to make sure, then this statement has nothing to do with the, adding Gauss-Bonnet, it has to do with the gap, or no? Like, so A is equal to C then should not be related to the gap of the spectrum, right?
No, it is related to the gap. So in bulk language, the statement is that, well, A minus C is the Gauss-Bonnet coupling, and the statement is that you have to have string-like excitations at the scale set by that coupling. That's in bulk language. In CFT language, what we're going to prove is that A is equal to C up to corrections where you have up to corrections which are suppressed by the gap to higher dimension operators. So the real statement is that A minus C over C goes as 1 over delta gap to some power, which I don't remember, some known power. Okay, so the first thing I'm going to do is just to define this operator as something that appears in the OPE, and then we'll explain what it has to do with lengths.
So CFT can also imagine a scenario where there is no gap. I mean, there is a gap, large gap, no other operator, but just that the spectrum of double traces is modified. I mean, having to do with the contact term in the bulk.
Yeah. And he's saying you will rule that.
It will, well, there are contact terms that don't affect this. I won't have anything to say about those, but there are contact terms that do.
Oh, that's what
There-
you mean. 4.1.
Yeah. Those will be left free. Yeah. Okay, so let me just say some words about the OPE. So if you have two scalar fields and you want to look at the stress tensor contribution to the OPE, then there's a really nice formula for this. So what I want on the right-hand side is the full operator contribution from the stress tensor. So this is sometimes called the OPE block. This is a nice formula. There's a coefficient which is set by the Ward identity to delta phi over CT. CT is the TT two-point function coefficient. An integral over some domain of T mu nu K nu. So let me explain what this integral is. I have a point. I'm taking x1 and x2 to be time-like separated. So there's some domain. There's some domain in space-time. There's a diamond in space-time, a causal diamond that looks like this. And sigma is the surface. Sigma is this surface here inside that causal diamond. So it's a surface that's defined in a covariant way from the points x1 and x2. And K is the special conformal killing. It's the special conformal killing vector, which is describes basically time evolution within this causal diamond. It's like it's sort of it's a combination of special conformal and time translations that gives you time evolution inside this diamond. Okay, so this is just a nice way to think about the contribution of the operator T to an OPE. And what I want to.
Sorry, just go back a just to make sure that I understand. I mean, are you also going to be saying something about the fact that if there are higher derivative corrections to gravity, then they have to something funny has to happen at their coefficient, the scale set by the coefficient.
Yeah, in gravity language, that's what this says, because this is the coefficient of the Gauss-Bonnet term. It's not necessarily saying something about all possible higher derivative corrections, but what it says is it tells you that if those higher derivative corrections affect the three-point function of gravitons, then there must be string-like new physics at that scale.
But that's for the specific higher derivative corrections that affect the
That are what?
that affect the 3 point.
That's right. That's right.
So this vector k, what happens to it at the boundaries of your causal diamond?
It's 0. Okay, so we're going to look at the.
Sorry, and one more question. Is there a logical derivation of this formula or some algebraic derivation? I mean, can you see logically that this is how the block should have been? Is there a physical interpretation of the right hand side?
I don't know of any explanation better than that it transforms correctly and has the correct singularities, which are really, I mean, that's really the definition, and that's how you derive it, and I'm not sure if you would want something more than that. It is interesting that this is also the modular Hamiltonian of region sigma. I don't know of a very deep way to think about that. It's basically because they're fixed by the same set of symmetry and scalings. I'm not going to use that. I'll just use this formula.
So just one more thing. What is K? Can you say once more? What is K?
K is a vector field inside this diamond that looks like this. And one way to think about it is that you do a conformal transformation that takes this disk to a half plane, and then it's the Rindler boost of that half plane.
And the implication is over all the everything inside the.
It's just over this surface here. Yeah. There's a different formula that's over the whole diamond that you can also use.
That's what I was wondering. That naively you would expect a bulk intake.
Yeah, so this is actually because T is conserved. So generally you get an integral over the whole diamond, the interior of the diamond, but when it's conserved, you can push it onto here. Yeah.
So that is always codimension 2, right? In bulk?
What?
No, codimension 1. This sigma.
Correct. Yeah. Okay, so I'm going to take kinematics where x1 is at the point u comma v. These are the null coordinates. x2 is at minus u minus v. And the Regge limit is the limit v goes to 0 with uv held fixed. Okay, so we take v to 0, but we keep the distance finite and fixed. In other words, we send these points together and off to infinity.
You just boost, right?
Yeah. Yeah. And what you should have in mind is that we're doing this is an operator statement. We're going to eventually evaluate this in some state or with some other operators, and these limits are being taken with everything else at order 1 fixed positions. So you can evaluate the this integral in the reg A limit, and that defines what I'm calling the length operator. Okay, so I won't go through the integrals, but if you just take this integral and you just simplify the integral in the reg A limit, and what you find, so we have the coefficient, we have a factor of u, so this is a big kinematic factor here, that's important. Then we have du prime minus infinity to infinity, d minus 2x over x squared less than minus uv, minus uv minus x squared over uv, t uu of u prime v equals 0 ix.
Sorry, one more stupid question. Was it? It must be clear, but why did the bulk integral happen only within the light?
There's a good reason for that, which is that you need the OPE to go as x12 to the minus 2 delta phi plus d at short distances. And if you do the integral this way, that will happen. If you had done it over all of space-time, then it would have the correct conformal transformation properties, but it would not have the correct singularity. And that you'd have to, the way to think about that is that it's contaminated by the shadow operator. So this is a way of eliminating the shadow contribution to the OPE.
So if you do the integral in the complement, you would get only the shadow? No other covariant.
I'm not sure if that's that simple. You may have to worry about what happens with the coefficient too. I'm not sure. Okay, so let's stare at this formula for a minute. So, well, first of all, this is this operator. Everything from here to here. This operator is the length operator, delta L, and what is it? Okay, so it's an integral over a null ray of TUU. That much of it is similar to the ANAC operator. The difference is that as we integrate over so it becomes this integral over this. So we get to replace these 2 points by an integral of the stress tensor over the null ray. The difference between this and the ANAC operator is that there's some additional smearing in the space directions. That smearing is is complexified. Okay, so this is a bit of a strange factor. This is an Ix here, and the reason for that is that, well, if we go back to here, all the way that you get nice OPEs like this one is with time-like separated points, and we're now talking about these points approaching from a space-like separated direction, and that's where that I came from.
There's no inside of the light code with this, basically.
Yeah, there's no inside unless you put an I in there, right?
Yeah.
Okay, so but this you can also you don't have to start from this. This is just you can also just start expanding out operators here, and you can compare this to the usual formulas for the OPE. So this is just a completely general fact about OPEs in this limit. This is a contribution of the stress tensor. That I is also the other important thing about that I is that if we didn't have the I there, then it would just be totally obvious that this is a positive operator. This would be just some transverse smearing of the ANAC operator, which you're adding up a bunch of positive things, so it's still positive. But what we're going to see is that, well, with this I there, if you imagine expanding this out in the transverse direction, there'll be it'll start with the ANAC, and then you'll have some positive things and some negative things, and it'll be sort of magic and require something special to happen for that to be a positive operator. The special thing would be having a theory at large n and a large gap, so the holographic theories.
By the way, Tom, the Lorentzian OP converges when it acts on the vacuum, right? But this has to be inserted in any state.
Yeah. This is when we insert this inside a state, this does not converge. So we're going to need a good reason to be able to use it, and I'll come back to that a bit later.
If this is going to be important, it would be great if you could explain it. I don't even know the statement that the Lorentzian OP converges only on the vacuum. Why that's true? If it's not important,
Well, whether it converges or not will not be so important. It is important that this is a small contribution to the OPE. I'll come back and explain that later. Whether it's convergent or not doesn't really matter for our purposes. Because if it's just an asymptotic expansion, that's fine. As long as it's small, I'll be happy to use this OPE, and I'll come back later to talk about whether it's small. Okay, so let me give the holographic interpretation of this operator. Why am I calling this the length operator? So the claim is that delta L is the bulk operator which is the integral minus infinity to infinity du prime HUU of u prime v equals 0, z equals minus root minus uv. So let me put my picture back up here. So if this is the CFT boundary, then the claim is that this is an integral. This is a bulk metric operator. So this here is an operator. Maybe I'll put a hat. This is the bulk metric perturbation operator integrated over exactly that path of the graviton that was important for these causality constraints. This isn't quite true. There's when you take, so there's a way of translating bulk operators to boundary operators, and well, we know of course the bulk graviton is dual to the boundary stress tensor, so a bulk metric operator could reasonably give something written in terms of boundary stress tensor, but the dictionary is not that simple. There are also multi-trace contributions to the bulk operators, so if you really take the bulk metric operator, you don't just get this. You also get multi-trace contributions. Let me sort of ignore those for now, and I'll come back to those later.
this will come from the free HKLL map. The HKLL map.
Even the
Even the free one has
even the free one would have TT double traces in it. Yeah.
So are you expecting J to be at the boundary to be related to TUU, right? But J is at minus.
Yes. Let me write the HKLL formula. So it says that HUU as an operator, put that hat again, is equal to some smearing integral of TUU in the CFT plus multi-traces. This is the general map between bulk operators and boundary operators. And what you're thinking of is if you go near the boundary, the smearing integral collapses, and the leading terms in the metric are just the same as some local leading local term in the metric is the same as the stress tensor operator. But if you push the metric operator into the bulk, that corresponds to spreading out the operator on the boundary. So there's some pretty simple integral. I didn't write all the kinematics here, but there's an integral formula that just gives you this operator in CFT language.
So I missed something. So that factor of minus UV minus x squared divided by UV up there in the x integral, that exactly is the boundary runner?
It's a little more complicated than that because, let's see, why is it more complicated? There's an extra direction that's been integrated over here. See, so actually the bulk to boundary propagator for the stress sensor is actually just 1. So this, the integral here is just 1. But what I've done is I've done the V integral. So I've taken this, plugged it into, so here's how you would get it. You would take this formula for H. You would plug this in here. Then you would simplify some of the U and V integral, and that would give you this operator.
Multitraces are explicitly known. Does it depend on the theory?
Yeah, let's see. That I suppose they're explicitly known, and I'm not sure if they're explicitly known in this formula language exactly, but they're explicitly known in the sense that if we take a Witten diagram with graviton exchange, we can read off, that includes this operator, and we can read off the double trace contributions to that.
So it's just that when you have a graviton exchange, when you decompose it to conform blocks, you get a single trace.
Exactly.
It's the same type of.
It's exactly the same. Yeah. Yeah. This is sort of an operator version of that statement.
But there you just get the double traces.
What?
There you just get the double traces.
Yeah, that's right. This is just double traces in a non-interacting case, and leading in interactions, you'll have to worry about the multi-trace for higher point functions or higher n, 1 over n. Okay, so why are we getting the length operator in the OPE? Well, I just derived it from this OPE block formula directly from CFT, but let's see why this is true more intuitively, just using ADS CFT. So the idea is that for a heavy operator with large dimension, ADS CFT tells you that you should be able to calculate 2-point functions using geodesics. So this 2-point function should be e to the minus delta phi times the geodesic length.
Is that delta integrated over all the transverse coordinates, all the x's?
This one?
Yes.
No, this is at some fixed x. Yeah.
Even that other stuff was also at. Yeah.
Well, it had a central x, which I had set to 0, and then it had that ix smearing around the central x.
So that's at that same fixed end.
That's the central x set to 0. Yes.
Yes.
So the WKB approximation for a heavy particle, like a heavy massive particle, just travels on a geodesic, tells us we should be able to calculate correlation functions this way. And since this is true in any state, we can really interpret this as an operator statement. Phi of x1, phi of x2 is e to the minus delta phi times the length operator from x1 to x2. And if you're in a state that's near the vacuum, so G mu nu is ADS plus H mu nu, then you can calculate this, you can just expand out this length and calculate the length to linearized order in the bulk metric, and you find phi is equal to 1 minus delta phi times the perturbative correction, the linearized length operator. And this is integral HUU over the geodesic. So this is the same length operator that we just found by CFT methods.
I'm sorry, x1 and x2 are bulk points or boundary points?
Those are boundary points. So this is a boundary correlator, but we're using now ADS CFT to calculate it.
Okay, and one, where do you get the 1 from?
It's this exponential.
So just, I see.
Yeah. So I'm,
So 1 over C, right?
sorry?
There's 1 over C in the OP of phi. Delta phi divided by C. That's in the length of.
Yes. I guess I've probably set an ADS length to 1 in one of these formulas, which would, I think here I've set some ADS length to 1. If we put the units back, then it'll fix it and it'll give us the CT.
Formula has e to the power minus n
Yeah.
times the mass. And between the mass
That's right.
there's RADS.
That's right. That's right.
Okay.
Yeah. Okay, so this is just to sort of explain how OPEs and CFT and bulk observables and everything fit together.
So does phi have to be the same operator? Is it always?
As itself?
Yes.
I believe so, yes.
Okay, good. So this one is like the vacuum in an OP kind of sense, is like vacuum contribution.
That's right. Yeah, yeah,
Expected.
yeah. This is really. Yeah.
So, why do you have to part out the IDs between? Like, why do you have to do it this way?
I'm just trying to derive the leading contribution of the metric or the stress tensor to this 2-point function. So I'm choosing to work perturbatively around the ADS background. In principle, a holographic theory has this entire nonlinear operator in its OPE. I think it'd be really nice to try to understand that. You can do it in 2 dimensions. I have no idea how to do it in higher dimensions. For example, if we plug this operator into the black hole, we should be able to see, into the black hole state, we should be able to see the correlator in the black hole background. If we had the similar thing for the stress tensor, then transport should be hiding in this operator as well. So there's a lot of interesting things hiding in the nonlinear part, but I'm just looking at the linearized piece.
Well, in the previous derivation of the OP, where did you assume that delta phi was large?
Yes, good. That was in this. That was hiding in under the rug when I was talking about the multi-traces. So for a heavy operator, the multi-traces are heavy because they're just 2 delta phi, and therefore suppressed in the OPE. Okay, so heavy operator. Another way of saying it is that heavy operators automatically move on geodesics. So they only give the single trace contribution to the Witten diagram or to the OPE. Light operators want to spread out like waves. They don't want to travel on geodesics. And that's where these multi-trace contributions to the operator come from, and we'll have to deal with those a little later. Other questions?
Sorry, and you've used the fact that the geodesic between on one side you had a particular line.
Yeah.
And you've used the fact that the geodesic for your setup is that line.
Yeah, so I've taken these into the reg A limit, and in the reg A limit, the geodesic is that line and gives us back the operator we had before. Yeah. Yeah, so this line is the geodesic connecting the 2 points that are reg A, that have been boosted to the reg A limit.
And it looks like it doesn't hit the boundary just because the boundary points are so far away.
That's right, yeah.
Okay.
For ANIC, you don't need a geodesic, right? You just need a null line with a fine parameter along the null line, or do you need, for ANIC you don't need a geodesic, right?
Oh, in the bulk?
Yes,
Um,
I forgot. I mean, is it?
I believe it does have to be a geodesic. Yeah, I believe it does have to be geodesic. Well, it's not actually known what's true about the ANIC in a curved background, but I believe the conjecture is for a null an achronal null geodesic.
In flat space, the ANIC is true only along a flat line, straight line.
Yeah, but that's also the only achronal null path, I think.
Yeah,
Yeah.
yeah.
In curved space, it might be more complicated. Okay, so the conclusion so far is that in any CFT, just by doing the OPE in the reg A limit, the correlation function psi 5x1, 5x2, psi. I'm going to normalize this by the 2-point functions. So this can be expanded in conformal blocks. The leading term is the identity. We're talking about the stress tensor contribution in the channel phi phi goes to t, goes to psi psi. Now we're supposed to include all of the other operators in the theory. And what we've done so far is to just calculate, is to just understand this block in the reg A limit. Okay, so what we've shown is that this is 1 minus delta phi over ct psi delta L psi. And then we have to add all the other operators. So this is completely general, only use conformal symmetry. Even though I've been using bulk language like length operator, that's just a nice way to think about it. And it's that operator that I wrote down. It's a smeared stress tensor.
So in the Lorentzi theory, in this reg limit for the OP, there are these other non-local, these light ray operators, which can occur. So is there a reason why this one gives the dominant contribution like this? NX operator is just one of a class of 8 operators.
Absolutely. So this is not necessarily the leading term, and that's what we need to worry about now. In fact, this in a general CFT in the reg A limit, this expansion doesn't even converge and doesn't even make any sense. Each term is bigger than the previous one, and we're far beyond the usual regime of validity of the OPE. So what we have to do now is to understand when this term actually dominates. And what I'm going to, well, I guess the way I'm going to do this is first I'm going to say that if this term, first let's just assume this term dominates. And I want to argue that this implies the length operator is a positive operator. And then we'll come back to the question of when this term actually is the dominant contribution.
So, when you say other operator, those are coming from plus dot 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 or from this T exchange?
These are from the plus dot dot dot. This is the full contribution of t, the full leading contribution of t in the Reg limit.
Can you tell me, why do you require a reg limit?
Why?
What is the point of taking the reg limit?
It's just a choice, a guess inspired by the kinematics of the bulk calculation that gave A equals C. I mean, maybe one way to see it is because of what the geodesic looked like that I just erased. So when you take the boundary points to the Reg A limit, there's some geodesic connecting those 2 points that goes out into the bulk. And when you take these boundary points into the Reg A limit, then the path connecting them is just this nice straight line that was a useful way to probe causality in the bulk. So I'm going to be brief about positivity because it would take me a while to get it right, and I know you've already seen this from Sendepen. So let me just sort of state the answer. The claim is that if these other operators are subleading, then delta L is a positive operator. This is derived using the causality sum rule of Sachin and Sendepen and I. The way it works is to I'm not really going to give enough details to make sense of this, but I'll just lay out the ingredients. So the way that this works is to so we've calculated, we see this term, the 4-point function. And what you can show is that you can extract, you can look at the kinematic dependence of this term, and you can extract it by a contour integral of the 4-point function. Okay, so you extract this term from G with a contour integral. And then you can do a manipulation of the contour to turn this into an integral of a double commutator phi comma psi, phi comma psi. This is an object also known as the double discontinuity. So we wrote a sum rule for contributions like this in terms of the double discontinuity of the 4-point function. And the double discontinuity is greater than or equal to 0 by unitarity. So that's all I'll say about it. We could talk about it more later if you want. But the things that are going in here are first causality. So where is causality coming in? Causality is coming in and deforming the contour. Okay, so causality is a statement about where it's a statement about where the branch cuts are, or where the branch cuts or singular points are in the correlation function, because those are what's responsible for commutators turning on. And therefore, it's a statement about where the correlator is analytic. And it controls whether or not you're allowed to do this contour deformation. So this step is causality. Causality is not really an input here. It's just a way of thinking about it. Unitarity is the only input, actually, because unitarity implies causality. But the way of thinking about it that I find useful, at least, is that this step is causality, and then this step for positivity is unitarity entering directly.
One quick question. You you can extract the coefficient of this conformal block using the inversion formula,
Yeah.
and that would produce that structure on the right.
Yeah, that's right. So
Can we think of this as direct consequence of the inversion? If I just wrote down.
yeah. Our sum rule, the original causality sum rule that we wrote, is the inversion formula in a limit where the kernel is. So there's some kernel here, and in the limit, in the kinematic limit that we're talking about now, that kernel is just 1, and is literally the same formula.
And this causality that went into that you say went into the derivation for the inversion formula is the chaos bound, is basically the chaos bound. Closing the contour there.
The chaos bound is not quite the same. No, I don't, well, by chaos bound, you mean the spin 2, you mean the growth, the rate of growth?
In deriving the inversion formula, there's a crucial point, some point where a contour is thrown away.
Yeah.
That seems to me the only place where structural features of the
Yeah. So there's a growth bound that's used in our derivation and in Karen Hewitt's derivation, and it's also used in the derivation of the chaos bound. It's this Cauchy-Schwarz inequality on the growth of the correlation function. Yes, that's an input to all three. It's not quite the same as the chaos bound, though.
I understand.
Is it?
It's
Yeah.
finite in chaos bound. But I mean, it's what the bound saturates to, right?
Yes, that's right. It's the chaos bound is well, we're upside down. The chaos bound is about this, and it's the late.
That's
yes,
right.
yes.
That's right.
That's
yes.
right.
But it seems like you're saying you use more. You use that. But when you say you've used causality,
Yeah.
are you using more than that Cauchy-Schwarz inequality? I want to see where that goes into the derivation of Karen.
It depends. I'm not sure if it's more. If we're on the complex z-plane, then there's, yeah, it is more. It is more. So that, okay, I'm not sure whether this will make sense. So maybe I'll just be quick and then we can talk about it later. But the quick answer is that we're worried about approaching the origin in contour, on the contour, sorry, the cross ratio plane. And the Cauchy-Schwarz inequality that people usually talk about tells you about the real axis. And we're sort of approaching this singularity from above. And okay, so like the boundedness as the boundedness this way and the positivity, these are statements usually about along the real axis. We also need to know that it's analytic in this domain here. For that, there's a somewhat more elaborate Cauchy-Schwarz inequality. At least the way we did it, I'm not sure if, maybe there's some way of doing it in their language. The way we did it was to take a point here and do a conformal mapping that sort of effectively puts it onto the real axis in some other frame, and then you can impose positivity, and then you can map back. But I think it's a bit more than the usual Cauchy-Schwarz people write down.
And I'll ask you later, just to ask, let's say, in the Princeton derivation of the Karen-Bohr formula, could you pinpoint where they do the analog of this?
I think it's just in the contour, in moving the contour.
Moving the contour. So
Yeah.
it's like the edges of the contour, something like that?
Well, there's two. If you have a contour like this, and you want to put it out here, and then wrap the cuts, you need two things. First, you need to be able to deform it at all, and then you need to be able to drop the arcs. So these are really two different inputs.
So just analytically.
Yeah, just analyticity. I would call that step the causality step. Yeah.
Okay.
Yeah.
Fine. Thank you.
Just one clarification. You said if other operators are subleading, does that necessarily mean that you've now gone to CFT with a gap?
I'm coming to that next.
And where do you use that when you show delta x greater than or equal to 0? Does that...
Because here I said that you could.
Because you don't have anything in that,
Well, the important thing was that this was the dominant contribution to G. So if this operator is the dominant contribution to G besides the identity, then we can do this manipulation by doing contour integrals of G. If this expansion is badly divergent, or the other operators contribute similarly at the same order or higher or stronger, then this derivation will break down, and we won't be able to say anything about positivity. So the status now is that if we can show delta L is the leading contribution, then we know that it's positive. Okay, so now we need to understand when it's leading. I'll argue that there are two situations which are related but a little bit different, where delta L really is the dominant contribution to the OPE. The first case is the light cone limit. And in this case, we don't have to assume anything about the CFT. Delta L always dominates in the light cone limit. This is what's going to give the ANEC. So the light cone limit means that we take UV to 0 after taking the light cone. Or, well, we could do it in either order. The way I'll say it, since we already have delta L, is that now we take UV to 0. OK, so in other words, we do this in addition to the Regge limit. So this is a limit V much less than 1 over U, much less than 1.
This is the limit that sends the bulk geodesic far away.
This sends the bulk geodesic close to the boundary.
Close to the boundary.
Yeah, yeah.
Close.
So why does it dominate? In the light cone limit, the OPE is a sum of terms that look like this, minus UV to the twist, delta minus L over 2. Times U to the L minus 1 times other things that I won't write. The point being that in the light cone limit, so UV is going to 0, so it'll be the operators of lowest twist that are the most important. Lowest twist, delta minus L. And although I didn't really give enough details of the positivity argument to explain why, but this whole argument for positivity, it works not just for the length operator, which is this spin 2 integral of a spin 2 stress tensor, but for anything of spin 2 or greater. Okay, so this will give you a sum rule for each spin greater than or equal to 2.
Would you be able to factor U to the power L minus 1 as a large
Yeah, it comes from the fact that um,
I'm saying just sending UV to 0 and taking the lowest twist doesn't. What does it say about that factor?
what does it say about?
U to the power n minus 1. So now you're going to say that in the expansion with all other terms, you are going to look at UV to the power delta n minus a by 2.
The reason it's spin greater than 2 is because if you want to pick off this term, then the way you do it is you fix this piece, and then you do a contour integral of g times u to the minus L minus whatever power we need here to make sense of this.
Just U to the power minus.
Well, it's really at around infinity, so that's why I'm confused about the that's why I'm confused about it. So it's a contour integral around infinity of this, and if we the sum rule just doesn't. Once you do these contour deformations, the sum rule just doesn't converge if you try to do it down to spins less than 2.
So here in the inversion formula, is it the same spin greater than 2 thing, or in the inversion formula as well there was this spin?
Yeah, same reason. Yeah.
But for the inversion formula, there was this that at the boundary, it depended on the on the arc it followed up, right? In some cases, it could have followed up such that the formula could have been analytic all the way up to spin 0.
That's true. Yeah.
But here, is there a way?
There's a similar statement here, which is, well, you end up with an integral of u to some power times d disk g, and the d disk has some bound, which allows you to go down to spin 2. But if the d disk is even smaller in some theories, then you can go all the way down to spin 0.
Is there a way to say, like, classify all the CFD where d disk will be have lower than that?
I don't know. I mean, no. I don't know how to decide in advance, other than by calculating the d disk, whether a theory will have a large or small one.
But supersymmetric field theories, you might imagine, will have small. Because every time you explain some high spin, there's some low spin partner. I mean, n equals y angles, I think we know does.
But even
Yeah.
some non-supersymmetric theory also show this kind of thing, right? Like the Chern-Simons with the fermion also shows the same.
He's in Gibbert's
Yeah.
calculation.
Yeah.
Yeah, there must be some reason.
So
Yeah.
you mean but a priori it doesn't, right? A priori you add these ambiguities and you're saying
Basically, the answer was that
to be able to set them to 0. Yeah. That would brought up with maybe some higher spin. Yeah.
Okay, so the spin 2 one is the one that we've been discussing, the stress tensor, and it's easy to check that for v goes to 0, the length operator just becomes the Anak operator. And we've argued that if it dominates, which it does in the light cone limit, that this operator is positive. So this is a proof of the Anak that goes through this length operator as an intermediate step. This is really just the same proof that we gave earlier. I'm just phrasing it now in sort of bulk language, as if we had some particle moving on a geodesic in ADS. For L greater than 2, then you can repeat everything that we've said about the stress tensor for higher spin operators of lowest dimension. So we get a constraint on the lowest dimension operator of spin 4, the lowest dimension operator of spin 6, and so on. In the light cone limit, the length operator, which is not really a length operator anymore, it's not the integral of it's not the geodesic length, it's a generalized version of that, but it will just give integral du x all u's, x u u u u u. So the claim is that this is a positive operator in any conformal field theory, and this we call it the higher spin NX. So this was a new prediction from this, and it applies in any conformal field theory, in particular in some of the field theories that people have been studying by Bootstrap. So a bit later, this was checked numerically in 3D Ising. Not the whole operator. You can't check that the whole operator is positive. But there's a very simple consequence of this higher spin NX, which you can directly check against the data that people get from numerical Bootstrap. And that is that all of the OPE coefficients of scalars with the operator x have to have the same sign. I'll say it has to be positive. You can flip the sign of x. But for some sign of x, all OPE coefficients to the lowest dimension operator of a given spin have to have the same sign. And that's been checked to high orders in the 3D Ising model. So this is a nice consequence of that.
So the bulk feature was that you had ADS plus H menu, and then you got this delta L, which was.
Yeah.
So instead of ADS, suppose I have a black hole.
Yeah.
And plus H menu. So all this thing will be exactly in your first talk here. You are showing transfer coefficient. You get the constants, right?
Yeah. So there are the positivity conditions that we get in the light cone limit work in any CFT and any state. Because just when I did this, when I argued that this was leading, I didn't have to say anything about what kind of state we were in. It's just always leading. Where I'm about to go to the A equals C case, in that case, the length operator is positive in large N theories with a large gap in states near the vacuum. So I think that there should, that if we were able to calculate the full general nonlinear length operator, we should be able to talk about a length operator in a black hole background, but it's not the same operator. It's not the operator that I wrote here.
Tom, just another question, which is there an analogous statement about a WKB limit of 2-point functions given as an exponential of not the geodesic length but some other stuff like delta times the length plus some other charge of these operators times.
If it's coupled to other fields, say. Yeah, I imagine that should work. We should be able to use WKB on the bulk field equations, whatever they are, and get an equation like that and generalize this OPE.
So it would be like delta times stuff coming from H and then the other charges and blah blah.
Yeah, I think so. Yeah.
Tom, I have a question.
Yes.
This formula you wrote for large n for gap series of the operator product of two operators being given by the length operator, which is an integral for the geodesic of the metric actually. So are you saying that if I take this the curve along which I evaluate this operator, go to the horizon and back out, it makes sense? You said that for a general state, you have this operator integrated along the curve.
Yeah, and the question is whether that can probe behind a horizon. Is that the question?
Yes, that's the question. Can it go in and come out again? Because these are evaluated at the boundary, right? So I start from the boundary, go inside the horizon and come back. Are you saying that I can do that type of calculation with this formula?
With a geodesic like this will always sit inside the entanglement wedge of a region that contains the 2 points. So if we have a region A on the boundary that contains the 2 points, the geodesic will always sit inside that entanglement wedge, and then yes, we can reconstruct that as a boundary operator. You won't, for example, be able to take two points on the same boundary of an eternal black hole and convince that geodesic to go behind the horizon and come back to you. Okay, so the other case where delta L dominates are theories with large n and a large gap. And in this case, if we're to write this OPE again, it looks something like 1 over n squared times the sum of our operators of u to the L minus 1 dot dot dot. We no longer have kinematic suppression. I've set u and v. I've set 1 over u and v to be of the same order, so I'm calling them both u. So we no longer have the kinematic suppression, but we have a 1 over n squared to save us. You know, in general, if we were trying to do the OP in the Reg limit, and we were not in a large n theory, we just couldn't. We would just fail right away because this contribution is bigger and bigger at higher and higher spins, and it's clearly just a badly divergent, not even asymptotically good series. But at large n, we can use this thing to control the expansion, and then work wherever we want in the kinematics. So that's why we're allowed to do this at large n. So that's what large n buys us. Large n buys us the ability to do the OPE in the Reg A regime. What about large gap? Well, that's what tells us that we can focus on the stress tensor here. Because
if you just had large n, I don't see how. I mean, you could have particles of arbitrarily high spin, even at a given order, 1 by n squared.
yeah.
So this would still not converge.
Yeah, you would have to. You have to resum them, and that can be done. That's what they do in this conformal Reg A theory.
Okay.
Yeah.
Sorry, so what does the 1 over n squared do? And various L's are still, all of them are multiplied by 1 over n squared.
Yeah.
So what does the 1 over n squared do?
Well, it's 1 plus. What the 1 over n squared does is it allows us to treat the contribution to the OPE as small corrections to the 1. And well, basically, it allows us to get a good approximation to the correlator by using the OPE. as far as the sum over spin, you're right, that if we really do the sum all the way up to infinity, the 1 over n squared doesn't help, it just sits out front. But these sums over spins can be resummed using conformal Regge theory, and then we have a good approximation because of the 1 over n squared.
So is it that some higher 1 over n corrections you can drop? Is that the point?
Is what the point?
Having 1 over n square there allows you to drop. Is there a plus dot 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 or the 1 over n to the 4 and so on?
Yeah. There are higher terms.
So is the point that you can drop them because of that 1 over n?
Yeah, you could say it that way. Yeah. This is something you could calculate with Witten diagrams. We don't have to say conformal Regge theory. We could say Witten diagrams. You can calculate the 4-point with Witten diagrams. You could calculate the 4-point function in any kinematics. You don't have to work in Euclidean kinematics where the OP converges. You can work in whatever kinematics you want. You calculate the Witten diagram, and that's a good approximation to the answer. Even though, once you take that Witten diagram and expand it in sum over operators, you're not in a regime where you would normally expect that sum to converge. It's the 1 over n squared that's buying you that ability. Doing the OP, it's like doing perturbation theory, and you need something to control the expansion. If it's not the kinematics, then sometimes you can use 1 over n. Okay, so far we used 1 over n. Large gap is going to bias the suppression of other operators. Now, so like if we do a scalar OPE, and we assume that the bulk theory just has a graviton and a scalar, then we'll get terms like this. But we'll also get an infinite sum of double trace operators. So those are a bit annoying. That means that if we go back to the causality sum rule and try to derive that something is positive, we'll actually get something like this. We'll actually get delta L plus spin 2 double traces is a positive operator. So if we just do this directly, if we just work with the position space 4-point function and use the OPE, then we get positivity conditions like this one. And these are not good enough. Okay, so this condition is true, but it's not good enough to get A equals C. And
So here delta L operator is different here. Like earlier already,
this is the same operator.
but already you had delta L to be greater than 0, right? Greater than 0. I'm sorry.
In the absence of this additional terms now there is this additional term.
Yeah, well, we're trying to prove that delta L is bigger than 0. But what I'm saying is that it's actually, in a theory, the point is that in a theory with a large n and a large gap, actually delta L does not dominate the Regge kinematics because there are also contributions from double trace operators.
You proved it only in the light code.
Right. In the light cone limit, this was fine. It dominated, and we got the NX immediately. But in the Regge limit, it's more complicated because in the Regge limit, there's this extra contribution to the sum rule.
So the higher twists contribute equally.
Yeah, there's an infinite number of contributions. Yeah. All at spin 2 because the sum rule involves a projection on the spin 2, but every spin 2 double trace will contribute to the sum rule. Okay, so that's sort of the hardest obstacle.
One time continuous complex. So these delta L operators, they depend on. I thought these are just fixed definition, but.
That's right. Delta. This is this thing that I wrote earlier. It's like integral minus uv plus x squared
But it depends
tu
on
u.
Oh, it depends on UV by this way.
If you try to just, if you work with, if you work in the light cone limit with large N and large gap, you don't get A equals C. You just get the NEC. You still just get the NEC, which is this range 1/3 to 31/18.
I guess it would be clear once this derivation is complete. Why the difference between the what? So here, what is it that the radial bias here is not
So,
clear?
well, let me say right now that if you can prove that, if you can prove this, you get A equals C.
How would that?
I'll come to it in a minute. But if you can prove this, you get A equals C. But so far, we get something worse. So far, we got that.
You said that the delta L operator corresponds to the geodesic length between 2 points x1 and x2. Can you understand this if you double traces in that language? There's some correction into that?
Yeah, you can. So if you think of that, if you think about evaluating this inside a 4-point function, in fact, maybe I was about to draw a picture that's related to your question. If you think about not as an operator, but you think about evaluating a 4-point function, and in this kinematic regime, then you don't get to put things on geodesics when you evaluate a position space 4-point function. You have to calculate a Witten diagram. And there'll be some graviton running inside this Witten diagram. And when you take a Witten diagram with a graviton and you decompose it into operators, there's a contribution from the stress tensor, but there's also the contribution from all of the double trace operators. On the other hand, if you have objects that travel on geodesics, and you calculate a diagram, a geodesic Witten diagram, which is just the same thing, but where we don't integrate the vertex over all of space-time, we just integrate it over this geodesic, then this corresponds to just the stress tensor block. Okay, so so to answer your question, when we just talk about the length operator, it's just this geodesic length. That's if you were to think about that not as an operator, but inside a 4-point function, that's like diagrams like this one. But what you actually calculate in correlation functions are diagrams like this one. And that's why we're getting this contamination from double trace operators. Fortunately, this also tells us how to fix it.
So in your Witten diagram on the top, if I were to think of, so we integrate these, so instead of integrating over geodesic, you're just integrating over all the space, right?
That's right.
But now can I understand that integral as being an integral over geodesic plus some corrections to it or something like that?
I don't know of any way to do it that way. I guess if the dimension of the operator were large, you could probably view this diagram as corrections to this diagram.
Okay. Okay, thanks.
Okay. Okay. So this is the situation. We're trying to get things to come from geodesic lengths, but we're calculating correlation functions, and we're getting all this double trace junk coming in. Okay, but this also tells us how to fix the problem, because and let's go back to chems for a minute. So they were calculating, they were thinking about gravitons propagating through a shock wave, and those gravitons were traveling. Those gravitons were plane waves. But you can think of them as as being more like the geodesic calculation. If you had a graviton traveling on a geodesic, then it would give what we want, and it would have the bulk time delay that we want, and it would give A equals C. But we know how to make gravitons go on a geodesic. We just insert wave packets of the graviton instead of inserting in position space. So instead of talking about correlators in position space, we should talk about correlators in momentum space, where these momentum space wave packets are smeared in such a way to cause that corresponding bulk particle to travel on a geodesic. Okay, and the point is that in momentum space, well, how do I want to say this? There's a formula like this. It says that if we insert a stress tensor wave packet with momentum p at point x1, I have both a momentum and a point, because it's important that this is a wave packet. So it's a wave packet centered at x1, point p. And then we have minus p at x2. Then this has a very similar OPE to the OPE that we saw in the Reg A limit, where there's the identity term, and then there's some coefficient times the length operator, and there are no double traces in this OPE in a large N theory. So intuitively, this is just, intuitively it's for this reason. It's that by working in momentum space, you can cause your particles to travel on geodesics. At the mathematical level, you just have to calculate it and see that you can project these out. So
So how does this happen? When I do this wave packet starting in the position space, let's say I integrated it with respect to a kernel, and then how is it that the double traces are projected out with that integrated?
I can't quite say it in this language because we didn't actually do it in the OPE. We did it in the 4-point function. It's a bit, I can explain it to you later in terms of the 4-point function.
So
It's,
this Venn diagram level, one can see that. At the 4
that's right, yeah. That's right. That's the easiest way to do it, is to do it on this Witten diagram and show that it turns this Witten diagram into that one.
But I guess the question is similar then. How is it then driven? I guess it happens at some technical level. Is there
What's a,
is there any physical intuition why
I mean, the physical intuition, I don't have anything better than what I just said, which is that I think using these wave packets localizes the contribution. So we're going to put TT here and put these in momentum space, and it's going to localize this onto a geodesic. So the contributions to the integral are really more like a geodesic Witten diagram. Okay, so
So for our external operators were any scalar operators. Now here we need to take them to stress.
yeah, that's right. So I was writing, when I was talking about the Reg AOPE, I was talking about scalars because it was much easier to write the formulas. With scalars, we could also just get rid of the double traces just by taking them to be heavy. But ultimately, in order to get the constraints, we need to use the stress tensor. We can't take it to be heavy. So that's why we're forced into this.
Sorry, and when you take the stress tensors on the outside and you boost them, do you have to boost the internal indices of the stress tensor as well?
In order to go into the Reg A limit?
Well, that's a choice.
Well, that's a choice. I can't remember. We didn't phrase it in exactly this language, so I'm not sure in that language whether we made that choice. I think not, because
To derive, if you wanted to derive some sort of growth bound for that, I think you would have to boost the internal indices as well.
I see.
I mean, in the chaos monk paper, if you try to do that thing with internal indices, I think you would have to boost everything. So that somehow feels natural to me. Was what
Yeah,
I
I think that we did boost the indices.
Okay, good.
I believe so. Yeah.
What do you mean boosting internal? You mean the tensor transformation of the?
Yes, we did. Because what we actually did is we calculated. We took two t's and two scalars. And what we really did is we boosted the scalars, but then you could boost back, and so you are going to boost the indices.
Yeah.
Yeah.
And what I mean is start with some fixed indices, and then boost not just the positions but also the indices.
Yeah. Okay, so I know I glossed over some of this multi-trace stuff. It gets a little technical, but the upshot is that by studying TT psi psi, TT scalar scalar, with the stress tensors inserted in momentum space, that you find the following positivity condition. That the length operator is in general, you would have to say that the length operator plus double traces are positive, but the double traces just are projected out by work in momentum space for the stress tensors. Therefore, the length operator itself is positive in these momentum states.
So, just to make a picture understand, I thought you were requiring OP expansions, right? Phi phi, how it is OP, like phi phi was 1 plus something plus something.
Yeah, yeah. So I've replaced phi by t now.
So in the then is it so you derive it in a different way? I'm saying in general momentum space OP does not work nicely there.
No,
Like-
that's true. These these points are not close to each other. These points. What I'm really doing is I'm using the position space OPE for points that are far apart like this, and then I'm smearing them like that. So I'm still allowed to use the OPE.
So this going to wave packets has now happened in the external states?
Yeah, delta L has double traces for all of the operators. And
And projecting out the double states is by working with appropriate external states? This epsilon dot
yes,
T.
that's right. That's right. I mean, you can do it with the other state if you like, but you won't. But you won't get A equals C that way. So
I thought the delta L is also coming from the TTOP where the T are the wave packets, right?
say that again.
The delta L is also coming from a TTOP.
Well, here I'm thinking of it in the following way. The scalars are creating a delta L.
Oh.
This includes in it double trace operators TT,
Okay.
but those don't contribute because they're not contained in this OPE.
Yeah. Delta L I'm thinking of just as a proxy for the stress tensor block.
That's right. Yeah.
So it's just whatever the block is.
Yeah.
As the double traces has them.
Yep.
So in this Witten diagram, if you just use the wave packets for the T,
Yeah.
you automatically get just a single block of T.
If you do that in this Witten diagram, then let's see. So if we have TT psi psi, where psi is a scalar, we'll get two.
Size are fixed position.
We'll get two sets of double trace operators.
Yes, T squared, psi squared.
These we're getting rid of by making psi heavy,
Okay.
because that's easier than going to momentum space. These we're getting rid of by inserting wave packets.
I'm going to try another sort of set of words that you tell me if this sounds reasonable. We know that, well, one way of thinking of roughly a double trace interaction, a double trace contributions can be modified by modifying a direct 4-point complete in the bulk.
Yeah.
So now if you aim geodesics so that they would all meet at the same point, that will just not operate.
That will what? It will.
That contact interaction will not operate. So if you aim your geodesics so that they hit 2 at a time, then you can only get exchange contributions and not contact contributions. Is this part of what's going on? Is it all of what's going on?
I think it's the exchange itself which is simplifying. The exchange diagram, written diagram, consists of at the level of blocks, double traces, which are what is being gotten rid of.
Yeah, I think it's more like it's. I don't think it's that. I think it's more like you want to sort of maintain a fixed. You want to maintain some impact parameter, so that you can go to small impact. The constraints really came from small impact parameter, and if you scatter with waves, you can't really go to small impact parameter. So if instead you get these things to travel on geodesics, you can tune the impact parameter of those geodesics at closest approach. And if you don't use web packets, you can't do that.
Maybe I can modify my question to ask, why aren't you seeing the direct 4-point exchange in this whole process?
What do you mean by the direct 4-point exchange?
Suppose I added a Riemann to the 4.
A vial to the 4?
Why?
Okay, yeah. Yeah, the reason we're not saying that is because
Isn't it because your 4 points aren't meeting at the same point?
yes, that's true.
If they were, you would see.
Yeah, although I don't think that.
In this way of doing things, you don't have 4-point function on gravitons, but just 2 sides, 2 heavy guys and these 2 T's. So it's not.
Okay, but suppose you had a psi tt 4-point function. I mean, psi squared Riemann squared.
Okay.
Why isn't your analysis sensitive to those terms? I think so. Must be. Like, keeping away from that they are hitting.
Yeah, I don't think those give terms that grow in this regime.
Well, but enough derivatives they grow. Is the growth just determined by the angular momentum? And with enough derivatives, you get very large angular.
I can't remember. Maybe I can. Let's come back to it after, because I can't remember what happens with those.
So can you say once more? So here the psi square, this double trace go away if you take psi to be heavy. How did you? So which one went away because you went into momentum space, and which one went away?
Yeah, these go away and these go away. Well, if we took all 4 into momentum space, they would all go away. A somewhat easier thing to do is to take just the t's into momentum space and take the size to be heavy. Because then these double traces are heavy and don't contribute, and these are momentum space and it doesn't contribute.
And it has to do with the Rieger limit, or suppose I had taken in the same in the light cone limit the same way, some things in the momentum space still nothing will contribute there anyway, like or these things will come back there. Like suppose I had done not in the Rieger limit but in the light cone limit, this going to the momentum space. Will the double trace come?
Then, let's see. Then it's a matter of twist. Okay, so then this just dominates.
So okay.
Yeah.
So it works
Yeah.
for all the.
Yeah. Yeah. Okay, so we were here. Okay, so this is just the geodesic length in this. Well, this is just the same 3-point function that you're calculating when you calculate the scattering through the shock wave. Okay, so. So you can. So you can calculate this explicitly, or you can go back through the pictures that I was drawing earlier of what delta L means. And this is just exactly, now we've really just translated this into the gravitational experiment. So this is just the same experiment that Chems did. And therefore, it's going to give the same constraints and gives you A equals to C. So that's the conclusion. So to sort of summarize, if you have any CFT, then you can put the ANAC operator here, and you get this range of A over C. If you have all these other ingredients that you can put in, large N and a large gap, then you just stick this other operator here. Really, all you have to do is smear the ANAC in the transverse directions with this IX. So you just put this other operator here, and that gives you the A equals C constraint. So you have a stronger condition in holographic theories, much like we saw for the Carty formula in 2 dimensions.
Wait, just to understand, I mean, if you would, once you do this algebraically, you've got this delta L operator which had a U in it. And all you do, I suppose, is take matrix elements in arbitrary states and process the positivity condition.
Yes.
And the condition that you get will depend on UV and becomes tighter and tighter as UV goes to infinity. Is this right?
Yes, exactly. Right. And it just is the same as this, except here you would phrase it in terms of the impact parameter. So by tuning UV, by tuning UV in delta L, you can tune the impact parameter of the bulk calculation, and you can get the whole range of constraints.
So where did a gap play a role here? Like I understand that expansion you took the phi square and t square term, but like I could have in this
You're truncating to the stress tensor block and double traces.
Yeah.
That's what it is.
Yeah.
So if I just truncate there, I mean, then I just get A is equal to C. That's the point. If I just truncate there,
Yes.
I just get A is equal to C.
Yes. Yeah, there could be another. I mean, in a CFT without a gap, there's some spin 4 operator that contributes and spin and higher spin. And
If there is a higher operator with higher dimensions, then it's not clear that A equals C fails by that 1 over that gap. Because
well, that's where it's allowed to fail.
the OP that you got who did not have any separation with respect to delta, just right, it was just U to the.
Yeah, the blocks themselves have delta dependence, so you can calculate the contribution of say the next high dimension spin 4 operator, and if you just calculate it, now you might worry about effects of conspiracies of many of them, but actually you get the right answer if you just calculate a spin 4 contribution, require that to be much smaller. You get exactly the right, what's believed to be the correct suppression of A minus C, which is, I think, delta gap to the 4.
So in this picture, what I don't understand, like, why are you, where do you require, where do you require UV, like bulk picture you said, like I have a impact parameter, which goes to infinity, this gives me A is equal to C, right?
The impact parameter goes to 0, gives
The
A
impact
equals C.
parameter goes to
Yeah.
0, that gives you A is equal to C.
Yeah.
So that impact parameter is same as taking the rigid limit, or this calculation is.
So there's a U in V here, and it's UV is controlling the Regge limit, and there's also there's also the positions where we inserted these wave packets are also playing a role. I've sort of inserted them in such a way that UV equals 1 corresponds to these hitting the wave packets at 0 impact parameter. So what you end up doing is sending UV near 1. It's like we've taken the wave packets and sent them at distance 1 from the ADS boundary.
So when this goes to 0, the impact parameter, you would get contact interactions also.
Sorry?
When the impact parameter goes to 0.
If it really goes to 0, then yeah.
We're taking the limit
Yeah.
separating
Yeah.
some of the wave packets smaller.
So some other choice of U and V corresponds to the light content. So it's just a tuning of U and V, which is just giving you various.
That's right. That's right. Yeah, that's right. And it's large N that allows you to tune up U and V, U times V.
Because you can drop off.
Right, right. Okay, so maybe I was going to write up some concluding questions, but probably I've exhausted everybody's.
No, we'd love to hear it.
Should we-
Hey,
this is-
totally, we'd
okay,
love to hear your
okay.
questions.
I'm gonna write the questions then. Maybe the rules, if I'm going to write the questions, are that we're not allowed to try to answer the questions. We have to do that at lunch. Okay, so there are a number of questions that this raises. Maybe one that can be approached even perturbatively. You know, we only talked about the 3-point function. A question that can be approached perturbatively is whether the full Einstein equations are unique. Okay, so we have our squared terms, our cubed terms, our the fourth terms, and so on. All we've constrained here is the HHH, graviton, 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 3-point function. So we've imposed two conditions on this infinite series, and we could ask whether the full series is uniquely fixed to 0. That's the suggestion of effective field theory in the bulk. We have neither a bulk argument nor a CFT argument for that, but it'd be very interesting to have one. The next question is, let's relax the gap condition a bit. So suppose we include something at spin 4. We know from the chaos bound that if you include something at spin 4, you have to also include an infinite tower of higher spin stuff. We also know that we can get reasonable answers by organizing that higher spin stuff into strings, into Regge trajectories. But more generally, can we constrain those possibilities? Okay, so the question, I suppose, is if we do have a spin 4 operator at delta 4, what are the possibilities for that theory?
What we really want to ask is string theory the unique classical completion of?
Absolutely. That's the question I really want to ask.
Yeah.
I'm going to guess no, but
Why?
I don't know. I don't know. Maybe.
Classically, they're all the same. I mean, the path of truncates.
Yeah, yeah.
Forecast.
What I think is an even harder question.
Are these all tied to 4 dimensions? On the question you're asking?
No, there's. This one requires d greater than 3 in the bulk. There's nothing to ask about 3D gravity. It's unique. But once we start including matter, 3D gravity is basically as interesting as higher dimensional gravity. So I think we could ask questions like this here.
So there's a point you're making. Where will you vacillate theory here then?
Where will vacillate theory? Yeah. Let's discuss it.
Okay, so the last question I'm writing is whether you can use any kind of similar tricks to derive constraints on the infrared effective field theory. In other words, not just on graviton scattering. These were about graviton scattering, but more generally, what are the constraints? Are there constraints on the infrared effective field theory, constraints on the matter content from consistency in the UV? And in particular, are there any constraints at all beyond the causality constraints that we sort of know about? This is basically the question I posed at the beginning of whether the swampland is a real thing, whether the swampland exists.
This is the bulk infrared effective field theory?
Yes, yeah, the bulk effective field theory. If I had to speculate about this, then I think there certainly are constraints. Maybe not on the infrared, but there are certainly constraints that can be derived by these bootstrap type methods. But it might be necessary to have more than just the correlators that we've been discussing. I mean,
is question 3 at large n or at finite n?
Finite. I think to derive constraints like this, we probably have to go beyond correlators. We need something like modular invariance to be able to talk about constraints like this. We need something like modular invariance in higher dimensions, because there are indications, for example, that for an example, let's take the question of whether a theory with a gauge field has to have charged states. So this is one of the most basic questions you can ask about UV constraints on what kind of field theories you can have and whether the swampland exists. That seems to be a constraint. If it exists, that seems to be a constraint that comes from consistency of cutting and gluing the manifold. That's how it works in 2 dimensions. The partial arguments for this in higher dimensions also are built on sort of cutting up the manifold into subpieces. But we don't really have the right bootstrap techniques to be able to ask that question yet. So I think that's an important problem.
How does that come from cutting into one consistency?
Well, what I really mean was modular. In 2 dimensions, what I really mean is modular invariance. I think the analog of that in higher dimensions is some kind of cutting and gluing of manifolds. Okay, thank you. Done.
Any questions at ICDS? Oh, we can't hear you.
Can't hear.
There's a button at the center of that funny shaped thing. Press that. When it's green, we should be able to hear you. It's green now, we still can't hear. Okay, if you shout.
We heard that.
The technical people have left. We can't hear. You can write your question on the blackboard if you want.
Is there a volume button?
I think he said he's giving up.
Okay.
Okay.
I think he's writing for the wrong blackboard.
Well, we can take our questions while he's writing.
Yeah.
Could I somewhere along this lecture, I just want to make sure the structure of your argument went this way. We had some independent argument that some 4-point function was positive. Then we approximated by some block. When that approximation works, that block has to be positive. Was that the structure of the argument?
Yes. There's a contribution, there's a certain growing contribution to the correlator that has to be positive. And
though you said it at the beginning, I forgot. What was the argument that the original thing had to be positive? Where was it just that it was a 4-point function of some square or something?
Where did positivity come from?
Yes, where the positivity.
No, it's not the square of anything. It came from this contour deformation. I mean, I only sketched it very briefly, but it was like, you take the, so there's a term in the correlator. Let's not talk about the OPE, let's just talk about the correlator, divided by the 2-point functions. Then in the Reg A limit, there can be a term with a u in it. Remember that u is growing in the Reg A limit.
Yes.
Okay, so this is not a bit, it's the same kind of term that appears in the chaos bound. So then there's this argument that involving integrating G and then deforming the contour, that you can prove that the coefficient of this growing term has to be positive. Okay, so if you look at the correlate in the Reg A limit and you see it look like this, then you can prove that this term is positive.
If I just try to use this inversion formula kind of thing, it turns this into a 4-point function of 4 stress tensors. Sorry, let me say it again. The 4-point function of 4 stress tensors, or 2 stress tensors, and two scalars, has a block contribution that gives you the stuff that you were interested in, this length operator.
That's right.
But you're saying that you need to do some work just to show that the part of the original 4-point function that you were interested in was actually positive. That is not visually obvious, just by looking at what 4-point function you're looking at. It's this stuff, right? You have to do some work to show this.
Well, you mean if you know the inversion formula, or if you don't know the
inversion.
If you know the inversion formula, all you need to use is that the d disk is positive.
So I see. You're saying that the expression that you calculate is manifestly positive.
If you know that d disk is positive?
Yes.
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 And that d disk is positive is because it's some square or something like that?
The d disk?
Yes.
It's not immediate. It's a square when you decompose, and you have to decompose it properly to see that it's a square. It's not directly a square. It's a sum of squares. So what you can do is you can take the d disk and you can slice Minkowski space into Rindler space, and see that in Rindler language it's a sum of squares. That's I think the cleanest way to do it.
Thank you.
The question on the board.
The other thing you can do is go to the T channel.
No, but it's showing something. Modular invariance in higher dimensions or something.
He wants you to comment on modular invariance at higher dimension.
Yes, modular invariance in higher dimensions. That's the question.
What does it mean?
There are, oh, no, that was my question. My question was how do we make sense of modular invariance in higher dimensions? There are certainly constraints on quantum field theories in higher dimensions that must be obeyed in order for the theory to make sense on different manifolds. And there have been just a handful of papers on this, and we don't have a very good way of organizing it or a clear idea of what those constraints are.